Well, hello. It's me again. I'm here to pick your brain for just a little bit. Hey, one of the ideas that we got really comfortable with a while back in the realm of energy was the idea about how rapidly you transfer energy from one type to another, or how rapidly we use energy, or how rapidly we transfer energy. That's an idea called power, and you probably know it again from a long time ago as energy over time. Well, I want to just make a connection between the idea of power mechanically that we've thought about and what we can do with energy electrical. Because now you have all the tools you need. I'm pretty confident that you have an idea about charge per time. And I think if you ponder that for just a minute, you might recall which idea that is. And I think you also have an idea about energy per charge. And I think that might be familiar as well. Charge per time, energy per charge. Now, wait a minute. What are those things? Charge over time. Well, that's, you know, coulombs per second, if we think of it in terms of units. And that's a name of a quantity called current, charge over time. Yeah. Energy over charge. Well, let's see. That's joules per coulomb. Yeah. Joules per coulomb. Those are capital C's, by the way. And energy per charge, of course, that's what we know now as voltage. So the interesting thing is what happens when you get them together. Well, what if we did this and we multiply these two things together? Notice what happens. We've got charge on top and charge on the bottom. Hey, bye-bye charge, which means the units coulombs cancel. And if we put that together, we're left with the unit which is joules per second. That seems familiar. Let's see what happens up here. Well, we're left with the quantity energy on top and time on the bottom. That might look pretty familiar too. Ooh, look at that. In other words, gosh, if you take current, electrical current, times voltage, electrical voltage, you get electrical power, which is really quite useful because, as you already are familiar, joules per second is otherwise known as watts. And you already know about current, coulombs per second. Well, of course, that's amps if we think about units here. And of course, energy per charge, that's volts. So what you notice is that we get power as the product of current and voltage. Now that becomes really useful. And it's with that little bit of information that I want to throw a challenge your way today. So ponder that for just a minute. Power is current times voltage. So if we think about that with a light bulb, for example, let's see what happens. Let's take this idea and let's apply it to a circuit that we've been thinking about. And that will give you a neat little challenge. So let's think about a circuit as we've been dealing with. Let's take just, a series circuit with two light bulbs. How about? Here's a bulb. Taking a break with a computer. And here's a bulb. Just pretend those are light bulbs. So there's a circuit with two light bulbs. And let's say we're dealing with 12 volts and 3 ohms for each light bulb. Well, the first thing we need to do is we need to figure out the total current in the circuit. We know the total resistance is the sum of the individual resistors. So we know the total resistance is going to be 6 ohms, because that's 3 plus 3. Wow, my computer has just gotten very slow. There we go. So the total resistance we know is 6 ohms. And we already know the voltage, which means with Ohm's law, we can first find out how much current flows. So going back to the things you've used earlier this week, we know that I, current, is voltage divided by resistance. So we can find the amount of current that flows in this circuit. So we know we've got 12 volts. And 6 ohms, giving us a current of 2 amps. Okay, if we know the current, that means we can also use that with our new concept to figure out the power, or you might call it the power draw. That is how many joules per second this circuit requires. So we now know the current, 2 amps. We know the voltage available in the whole circuit is 12 volts, which makes it look real quickly like the power of this circuit is simply 24 watts. Now, if you went and worked through each bulb individually, you discovered that each bulb uses 6 volts of the 12, so each bulb individually is 12 watts. But the neat thing is we can use this idea pretty straightforward to find an electrical power. So in other words, that tells us, just putting together Ohm's law and the power concept, how much energy per second is used in a circuit. So that's the setup for a little challenge. Consider this. We now know electrical power is current times voltage. You also recognize simply that power means energy over time. When you get a bill for the electricity at home, are you getting a bill for the amount of energy per second you use, or the total amount of energy you use? Well, I don't want to spoil it for you, but I'm going to tell you, you're getting a bill for the energy that you use. And that energy is determined real quickly by taking the power consumption at any particular time times the amount of time you use it. So for example, if I had that 24 watt circuit I was just using, and I used it for, 30 seconds, I could figure out the total amount of energy that I used. Well, 24 times 2 is 48, times 3 must be 72. And that's watts times second, or joules per second times second. So this circuit used 72 joules in 30 seconds. Wow, that's a lot of numbers. That's a large number for 30 seconds. But the truth is, if you're dealing with things like light bulbs, or things like an entire house of energy consumption, or heck, an entire school building, instead of watts and seconds to give us joules, we're going to use some other units. And the reason is, boy, think about how many watts a school draws, maybe thousands of watts at any particular time. And you multiply that by the total number of seconds we'd use them even in a day, you're going to get a giant number over here. So what happens instead is we use kilowatts and hours for power and time. And as a result, we get energy in a unit called kilowatt hour, like so. So let's say you used, 1,000 watts, 1 kilowatt, and you did it for 60 minutes, 1 hour. Well, that's a unit of energy that's simply called 1 kilowatt hour. Of course, if you had 2 kilowatts for an hour, it'd be 2 kilowatt hours. 2 kilowatts for 2 hours, it'd be 4 kilowatt hours, and so forth. Same concept, energy is power times time, but a unit that's more useful. So that leads me to the challenge. Check out this graph. This is some data that was collected in our school by me. It's actually being collected most all of the time. And if you look real closely, you'll discover the timing. February 22nd, 2018. This is 4:02, as in 4:02 in the morning. This is 10:43, as in 10:43 in the morning. This is 17:23, in other words, 5:23 p.m. And this is 004, in other words, roughly midnight. So what you notice is this data spans roughly 4 in the morning through midnight. Here's my challenge. Number one, notice what this is a graph of: power versus time. And you'll notice over here there's a blue plot that says south, a green plot that says north, and an orange plot that says total. And you'll also notice the units on that graph says power total in kilowatts. What I would like for you to do is attempt to figure out from this graph what amount of energy in a day. Now, it's this particular day. It happens to be February 22nd of 2018. But I'd like you to use this graph to see if you can figure out the amount of energy that our building used in this day. Now, you're going to have to estimate a little bit because this graph squiggles around a little bit. But let's see. If you have power on this axis and time on this axis, and you need to multiply power times time, I feel like multiplying a height times a width, if it were a real boring graph, would give us something like a nice little area. Well, that's still what you need to do, but it's a funky shape, so you might need to chop it into little pieces. But I'm going to leave you with that. Can you try to come up with the total amount of energy that this particular day saw used? Here's a hint. The units you end up in should be kilowatt hours. So I'm looking for you to come up with a rough estimate from this data of how many kilowatt hours of energy in this day. And then finally, what's the price tag? Do you know that Xcel Energy or Frost Benco charges us approximately 12 cents for every kilowatt hour of electrical energy? That's about what it costs, particularly in our homes, about 12 cents per kilowatt hour. So to wrap it out, your goal is to try to come up with how much energy in this particular day. And then once you know that, I'd like you to come up with how much money did our school spend just for electricity on that particular day? Because now you know the price per kilowatt hour and you can tell how many kilowatt hours. I'm looking forward to your feedback. I'm looking forward to hearing how it goes. Feel free to throw some questions at me, talk to each other, work together. But let's see if you can get something posted in there to talk about how that's going. Thanks. I look forward to hearing how your brain does with that.